Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for course schedule problem. Let's look at the problem description. We have to take a total of num courses which are labeled from 0 to the num courses -1, and we are also given with the prerequisites like which course should be taken first and which one should taken next as an array of integer with length 2. So if you want to take course A, we have to first take the course B. Okay, so we have to return true if we can finish all the courses, otherwise we have to return false. Let's take a look at this example. Here the number of courses is 2 and the prerequisites is 1, 0. That means if you want to take course 1, we have to first take the course 0. So in this case there are no other dependencies, so we can complete the two courses which is in name indexed 0 and 1. So we return true. Let's take a look at the example 2. So in this case the number of courses is 2, but the prerequisites has 2 entries. One in the first entry, the course 1 depends on course 0, and in the second entry course 0 depends on course 1. In this case it's like a loop, so we cannot complete both the courses, so we have to return false here. So the total number of courses is ranging from 1 to 2000, and the prerequisites array length is 0 to 5000, and each element in the prerequisites array is of length 2, and the numbers A and B will be less than num courses or greater than or equal to 0, and all the pairs in the prerequisites array are unique. Let's take a look at the approach to solve this problem. We can model this problem as a graph problem, especially a directed graph problem. In that each course can be viewed as a vertex in the graph, and the prerequisites can be viewed as an edge. For example, in this case, in order to take course 1, we have to first take the course 0. So there is an edge between from course 0 to 1. In order to take course 2, first we have to take course 0. So there is an edge from 0 to the course 2, and like similarly the rest of the vertices are connected in the graph. Okay, so we can view this as a graph, but how can we check whether all the courses can be taken? So when we traverse the graph, if you are able to visit all the nodes, then we can conclude all the courses can be taken. So we have to do a DFS traversal on a directed graph and check whether there is a cycle in that graph. How can we find the cycle in the directed graph? We can use the time stamping technique. So for example, when we do the depth first search traversal on this graph, and we start the traversal from the node 0, first we traverse node 1, which has the neighbor, which sees the some neighbors 3, so visit here, and then neighbor 4, visit here, and then return back, and then visit the another neighbor for 0, and then finally return back. Okay, we can see the DFS traversals output as a tree like this. So there are two arrays we have to maintain. One is for storing the arrival time of the node, and the other one is for the departure time of the node. As we traverse, we incrementing the global timestamp and save that value in that corresponding array. For example, when we enter the 0, we increment the time from 0 to 1, and we save this in the 0th entry of the arrival array, and then we see the node 1. So we try to call the DFS function recursively, and in that function we increment the timestamp, which becomes 2, and we save that in the arrival array. So as we go make a as we process more and more neighbors in a depth first manner, finally we will come return back. If there is no neighbors in this node, we will return back to node 3. At that time we update the departure time, increment the timestamp, assign the departure time of 3. Here assign the departure time of 1. And then when we come here, there are still one more neighbor pending. So first we visit there. So we update the arrival time. Then when we come back, when we return back, because there is no neighbors, we increment the time to 10 and we assign that value as the departure time of 2. And finally we comes back to the node 0, where we set the departure time to 11. Hence we are able to traverse all the nodes in this graph. There is no cycle. Next we see an example graph which has a cycle in it. Okay, and let's see how we can detect the cycle in this graph using this arrival and departure timestamps. Okay, so when we do the DFS traversal, whenever we visit a node, we update the arrival timestamp. Whenever we leave that node after processing all the neighbors, when we return back, we update the departure timestamp. So in this case, we start with timestamp 1. After processing 1 and 2 on all its neighbors, when we come back here, finally when we return, we update the timestamp 11. Okay. So here if you see, first we visit 0, update the arrival timestamp 1. Then we see a neighbor 1 and 2. First we visit the neighbor 1 and update its arrival timestamp as 2. And we see it has one neighbor, so we call another DFS function, and there we update the arrival timestamp of 3 with 3. Then we see another neighbor for 3. Then we see 3 has neighbor 4. Then we update the neighbor's 4's arrival timestamp as 4. And then we see the 4 has a neighbor 1. So after processing 1, then only we can update the departure time. Okay, so we are trying to process the node 1, but we see the node 1 is already visited, and if the node is already visited and processed, then it should have a departure time set. Okay, so whenever we see a node which is already visited but its departure time is not set, then that indicates a cycle. For example, in this case, we have the current node 4. It has neighbor as neighbor 1, and when we check the neighbor's departure time, it is 0. It is not yet set. So that means there is a cycle. So we can see from 1 to 3 to 4 and back to 1. It is a cycle. So this is the condition we have to check in the DFS traversal code. If there is a cycle, we return false and propagate that return value all the way back to the root node and return the final status, whether we can take all the courses or not. I listed out those steps here. First, we can perform the depth first search traversal on this directed graph, and each course is a vertex, and the dependency is an edge. So when we perform the depth first traversal, we check whether there is a cycle in this directed graph. If there is a cycle, then we return false. If there is no cycle, at the end we return true. And in order to find the cycle, we need to keep track of the entry and exit time of each node whenever a particular node is processed. Let's look at the flowchart. Input for this procedure is the num courses and then the prerequisites array. First we initialize the visited array, arrival array and departure arrays, and then we initialize the timestamp variable. Okay. The next thing we do is build an adjacency list based on the prerequisites array. Then we loop through all the vertices in the input, check whether they are visited already. If it is visited, then we skip it. Otherwise, we make a recursive call to the DFS procedure to process that current node. We pass the adjacency list, visited array, arrival array and departure array and the current timestamp, address of the current timestamp. When it returns, we assign that return value to the retval variable, and we check whether the retval is false. If one of the DFS returns false, we should break out of this loop and return from this function. And so we check whether it is false, then we immediately break out of the loop and then return the retval value. Otherwise, we keep processing the next vertex in the graph. Why DFS traversal begin with all vertices? Because sometimes the graph may not be connected, meaning some courses do not have any dependencies, only few courses have dependencies. In that case, we have to make sure we visit all the things. So that's why we loop through all the vertex in the graph and initiate a DFS traversal. Next, we look at the DFS procedures flowchart. So input for this procedure is vertex, visited array, arrival array, departure array and timestamp variable. Okay. So first thing we do is increment the timestamp and update the arrival of the current vertex with that timestamp. Then we mark that particular vertex as visited in the visited array. Okay. Then we get the neighbors of the current vertex and we process all the neighbors in this loop. So is the current neighbor already visited? Then we can check whether that neighbor's departure time is set or not. If it is not set, that means that indicates a cycle. So we set the return value as false and return. Otherwise, we keep processing the next element in the neighbor list. So if the current neighbor is not visited already, then we make a recursive call to process that neighbor first and assign the return value. And we check whether that return value is false. If so, break the recursion and come out and increment the timestamp. Before leaving the function, we have to update the departure timestamp of the current vertex. So that is what we are doing here. So yeah, so this is an extension to the standard DFS code. So check whether the departure time is not set for the neighbor which is already visited. This is the condition we use for detecting the cycle in the graph. Let's move on to coding. First, I define the constants for getting the index of the first course and the second course. So first course is present in the index 1 in each prerequisite entry, and the second course is present in the index 0. So that's why I define that constant. Next, I define constants for the visited or not visited state. So for not visited, I set to 0 and visited, I set to 1. Next, I initialize the timestamp to 0 and the return value to true. Then I initialize the visited array, an array of int. As I traverse the node, I set the corresponding index in this array. Similarly, there is an arrival array to keep track of the arrival timestamp of the node, and the departure array in the adjacency list. So this will help us to get the neighbors of a given vertex. First I initialize the adjacency list. Next I am building the adjacency list by traversing the prerequisite array. I am getting the first course ID using the index first, and the second course ID using the index second. Then I update the neighbors of the first vertex. In this for loop, I initiate the DFS traversal from each node in this graph if that node is not visited already. So if the visitor of that current node is not visited, then call the DFS function. The DFS function takes the vertex, adjacency list, visited array, arrival array, departure array, and the timestamp address. If the return value is false, then I break out of the loop, because the DFS call found a cycle. And finally I return the red value. Next I am going to implement the DFS function. First I initialize the retval variable to true. Next I mark the current node as visited in the visited array. Then incrementing the timestamp, and then I set the current timestamp as the arrival time of the current node. Next I get the neighbors list from the adjacency list data structure. Then I range over that neighbors list, and if that neighbor is not visited already, then I make a recursive call to process that node. If the current neighbor is not visited, then I make a recursive call to the DFS function. to process that node. Else here I check the return value of the DFS function. If it is false, then I break out of the loop after setting the return value to false. Else I check whether the departure time of that neighbor is set or not. If it is not set, that indicates a cycle in the graph. So in that case also we have to return false. So I set the return value to false and break out of the loop. This is to check whether there is a back edge present in the graph. Back edge is the one goes from children to one of its ancestor. So when we come back to this function after the previous recursive call, then I increment the timestamp and set the current timestamp as the departure time of the current node. Next I am going to run the test cases. Oh, some test cases failing. I think the input may have the cases where the start and end course number are same in the prerequisite array. So we have to check if both are same, that is also cycle. So we can return false while building the adjacency list. Okay, one test case passed, but still one is failing. Oh, this should be in the else part of the not visited if block. So if the node is visited already, then we check whether the departure time of that neighbor is not set. So let me rerun the test case. Okay, all the tests passed. Next I'm going to submit this program. Cool, this program is accepted. Next I'm going to do the code walkthrough with sample input. Let's do the code walkthrough for this input where the number of courses is 4 and the prerequisites contain the dependency between only the courses 0, 1 and 2. It doesn't include the course 3. So we have 2 components in this graph. When we call the can finish function, we initialize the timestamp to 0 and the return value to true. And all the 3 arrays are initialized with 0 and we build the adjacency list based on the prerequisites array. So 0 has a neighbor 1 and 1 has neighbor 2. 2 and 3 do not have any neighbor. Okay, so we build the adjacency list and then we try to do the DFS traversal starting from each and every vertex if it is not visited in the graph. Okay, because if you see here, if we just start the DFS traversal only from this node, we only visited these 3 nodes. There is no way we can traverse this. So in order to traverse all the nodes, we will have to initiate the DFS traversal from each node. if it is not visited. Okay, so that's what this loop is doing. So whenever that current node is not visited, then we initiate a new DFS traversal, and in frame 0, in the iteration 0, we start the traversal with the node 0. Okay, current value is 0 in the DFS. The current value is 0 and the timestamp is incremented from 0 to 1. So that's why we see 1. And this current node 0 has the neighbor 1. So the neighbors list is 1. And the return value is initialized with true. So this is what we do whenever we visit a node first time. Then we get the neighbors list, and then we ranging over the neighbors list and check whether that neighbor is already visited or not. If it is not visited, then we make a recursive call to process that neighbor node. Okay, so in this case we make a call with node 1, so the frame 2 is formed. Frame 2 is formed. So the current node's value is 1 and the timestamp is incremented, so its arrival time is 2. So that we can see here for the arrival time of node is 1, arrival time of node 0 is 1, arrival time of node 1 is 2. Okay, and then this has a neighbor 2, so that's why we see the neighbors list 2. So once we see that, we try to make another DFS recursive call to process the node 2, so the frame 3 is formed. So the moment we enter, we update the arrival timestamp of that node 2 and mark it as visited, and then we try to get the neighbors list, but for this case this do not have any neighbor, so that's why it is empty, and we initialize the return value to true. Then we once we because there is no neighbor, we come back, we are about to return back from this function. At that time we increment the timestamp and update the departure value of that node 2. So if you see, the departure value is from 3 incremented, so the new timestamp is 4. That is the return time of this node. So from here it starts from 1, 2, 3. Now we are returning back, so the return time is we are started updating the return time. So now it is 4. Okay, so when we return back, now we comes back to the node 1. So where we again there is no other neighbors, so we are about to leave from the node 1. So we increment the timestamp and update it in the departure time entry for that node. So here we can see 5. After that, when we return back to the frame 1, where we are updating the node 0's departure time. So we update 6 here. Then finally we comes back to the can finish function, because this traversal is done, this DFS traversal is done starting from node 0. Then in the next iteration we try to perform the DFS traversal starting from node 1. We check whether that node is already visited. Yes, it is visited, so we skip that, and then we try to do from node 2, that is also already visited. Node 3 is not yet visited, so we are initiating a new DFS call with node 3. So when we enter, the current node is 3 and we update the arrival timestamp, we increment from 6 to 7. So we update the arrival timestamp of node 3 as 7. Because this do not have any neighbor, it's only a standalone node, So we return back. While we are returning, we update the departure time of node 3 by incrementing 7. So we set 8 as the departure time. At the end, we visit all the 4 nodes. Then finally we return true, because in this case there is no cycle. So we finally return true. Next I'm going to do the time and space complexity analysis for this solution. Let's do the time complexity analysis for this input. The number of cores in this case is 4. There are 4 nodes in the graph. We have to visit all the 4 nodes in order to declare whether all the courses can be taken. So for n number of nodes, we have to traverse all the n nodes. So the DFS traversal algorithm makes sure each node is visited at most once by doing these checks. So the time complexity for this procedure is order of n. The space complexity for this procedure is also order of n, because we need to allocate space for n number of elements in the adjacency list and visited array, arrival array, and the departure array. So the space complexity is order of n. Thanks for watching this video. Have a great day.